Hi all. Thank you for sticking to the very end. I'm here to talk about how to deploy machine learning models using serverless AWS. Just a brief introduction first. I am from Brazil, and now I've been based in Dublin for the past 4 years. And currently, I'm staff machine learning scientist at Intercom. And by the way, we are hiring for machine learning roles, so if you're interested, come talk to me later. We have roles for science and engineering here in London, also in Dublin, and at the senior and staff level. So we have plenty of roles open. And why is a machine learning scientist here to talk about serverless? Well, the story begins a few years ago as my first data scientist job. I was tasked of creating a model to combat a credit card fraud. Long story short, I built a model that would deliver a nice increase in profits to the business, but I couldn't deploy it. We had to bring in a machine learning engineer to build a fancy deployment server in Scala. And the reason is simple. The company would only allow JVM languages in production. Python was not allowed. Unfortunately, that's a reality for many companies out there. And I thought there has to be a better way. So after learning about Lambda, I thought I could solve this problem for other data scientists, and I created a deployer, which was a solution, and the pitch was from model to endpoint in just one click. I'm not trying to sell deployer here. It was a failure, it's long gone. Even getting this screenshot, I had to go to the web archive. But deployer taught me many valuable lessons, some in business and some in model deployment. And I intend to share with you the second part. We can talk about business later, which is how you can go from a model. Here I show scikit-learn, but could be XGBoost, LightGBM, TensorFlow, whatever, to a REST API endpoint in 3 steps, which are reasonably simple. First, you pickle the model. Then you create a Lambda function that gets this pickle and calls predict. And finally, you wrap this Lambda function with API gateway as an endpoint. Before we get to the actually serverless, let's clarify the terminology here. What do I mean by a real-time model? This is a model that responds to predictions instantly or almost instantly, generally one at a time as they come. The prototypical real-time application for machine learning is a Flask server that communicates with the main application, so it's a microservice with REST API. The main application, which could be, for example, Ruby on Rails, calls this predict endpoint. The Flask calls the model and returns a HTTP response. The first takeaway is that if you can use this framework, this architecture, just do it. There's no shame using a battle-tested technologies. And what are batch models? As the name implies, they serve predictions in batches, and they're generally embedded as part of the data pipeline or the ETL. So a prototypical batch model would live inside, let's say, an Airflow pipeline that runs with Spark. Or you could have something with dbt and Snowflake. And another takeaway is that if you can use batch models, you should. They are much, much simpler to maintain and understand than real-time models. And the reason for that is that you train models in batch. I'm not saying that you train models inside the data pipeline, but you train models with some kind of data frame that must come from somewhere, and that's generally the data pipeline. When you have real-time model, you have 2 big challenges. The first one, you got to ensure that the serving pipeline and the training pipeline are the exact same. And that's, in my experience, not easily done. And secondly, you need to now maintain and scale a web server, which is definitely more difficult than maintaining a processing step in the data pipeline. But of course, for some applications, it's inevitable to use a real-time model. This is an assumption you should test empirically. You should really test whether you need a real-time. You should test a model using just day-old features. And sometimes, for credit card fraud, you're going to find that there's no way you can ignore the online information. And now, if you cannot just go with a Flask server, I'm going to present an alternative way with some pros and cons. We're going to go over the trade-offs later. So first, who here knows roughly what a Lambda function is in AWS? Please raise your hands. And who here has actually invoked a Lambda function in your life? Okay, so I can be quite quick on what Lambda is. It's a way to run Python functions on the cloud. So serverless is misleading. Of course, there is a server somewhere, but that's not going to be managed by you, so you don't have the hassle of creating, managing, and maintaining a Python web server. It has some strong scalability. You can have up to 1,000 concurrent runs by default. That's for all your Lambda functions, not just one. And you can increase that, of course. and you only pay for what you use. So roughly as a rule of thumb, and don't quote me on that because those numbers can vary depending on your exact use case, you spend $1 to handle 1 million requests. So that's pretty good, right? Like, if you have a Heroku server running, you're going to pay at least $10 monthly, and here you could be serving 10 million requests. So how do you actually go from like a Lambda, a code to a Lambda function deployed? Here's a minimalist, but this example would work if you just added the imports. And it's quite simple. So first, we load the model pickle. And second, we have a predict function. This is called, in Lambda parlance, the handler, which has two arguments, event and context. The context is metadata that Amazon provides to you, such as memory limits, function name. Event is what really matters here. It's the argument that whoever is invoking the function is going to use to pass you like a parameters, payload, or whatever. And then we just parse the event input. We call model predict on X, the features, and we return the output as a JSON string. And that would work already. And you have two ways to deploy this. One is by using a zip file method. The other is by using a Docker file. Zipping Lambda function was the traditional initial way to do things here. And that's how I originally started. But I got to tell you, it's very, very difficult to get this right because for machine learning, you have a lot of dependencies, and this might blow up your zip file. There are some very strict requirements on the zip file size, and you must insert into the file all the dependencies like NumPy, scikit-learn, pandas. So most of the time I spent on deployer was handling this, hacking my way around on minimizing the zip file size. But now we have Docker files. So you can do like your library dependencies with just pip install requirements. It's much simpler, and the limits are much looser. You also get reproducibility. So you can run your Docker image locally and just see the behavior as you would see in the cloud. So definitely go with Docker. And how does the scalability aspect work exactly? Here's an animation by AWS itself, and we have 10 requests in total. When the first one comes, you don't have any computing instance available, so AWS has to spawn a new instance. And there's some latency payment you have to make. You don't have to pay like in money, but you pay in latency terms. And there's going to be some higher delay in the first invocation. And as more requests come, and the first one hasn't finished, you have to like spawn more instances, and you're going to have like this spike in latency. But Amazon controls this for you, so all the scalability, you don't have to worry about it. It just works. And what is nice that in subsequent invocations, you can reuse the already spawned computing instances. So for request number 6, it's going to reuse the first one because, well, the first one has already finished. How long does it last? This is not something you can configure. This is kind of hidden, but a rule of thumb is that instances stay alive for roughly 10 minutes. You can keep them alive by just pinging like dummy requests, but there are really no guarantees it's going to work. Or you can have what they call provisioned concurrency. So you have some functions always warm, always ready to be used, but of course you pay for it. So yeah, I'm not sure if I would advise unless you need it. The second part of serverless my presentation is about API gateway. This is actually optional. You don't have to have API gateway to serve models with Lambdas. If you just invoke the Lambda function directly, you can skip this part. But if you want to distribute this with outsiders, like people outside the organization, you need some REST endpoints, and API gateway provides you that with a lot of interesting functionalities. So you should control usage and distribution, and also access. And you can do so by defining API keys with different usage plans. So you can have one API key with a particular daily quota, rate limits, throttle. For example, you can have different business plans. Each one's going to have a different API key with different powers. And again, you just pay for what you use. It's slightly more expensive than a Lambda on average, but you get the first million requests for free every month. To understand the whole architecture, it's nice to go look over the lifetime of a request. This is quite similar to the real-time model using Flask, only the middle is different. But we start again with a post request on the endpoint. This is going to be handled by API gateway, which is going to seamlessly call your handler, in this case, predict, and it's going to get the payload from the predict, and it's going to insert that into the event argument. And now your Lambda is going to call the model, predict, return the prediction as a dictionary, which is going to be parsed as HTTP response. So you can set the status code to 200 if it worked, or 400, 500 if there was a failure. And then my application is going to get the request back. So you might have heard that like serverless is just hype, and this tweet and blog post from DHH, the father of Ruby on Rails, made rounds recently. And the reason that he was inspired to write this blog post was with the news that Prime Video, so Amazon itself, was giving up on Lambda for some use cases. And the reason for this is that Amazon has such a high scale, high volume, that Lambda is not cost effective anymore. They do have to pay internally. It's not the same prices as the public ones. I was talking to like a friend, AWS engineer, and he told me there is some accounting internally, and you end up paying for what you're using. And for some applications, Lambda is just not cost effective. But there are some good reasons. I'm going to go with the cons later, but first I'm going to try to sell what are some good use cases for Lambda and API Gateway. The first one is that you're a data scientist and you have a Python model ready to be deployed, but for some reason Python servers are not allowed, or there's some friction or resistance and you don't want to play politics. Or maybe you're an indie hacker and you want to create like a side hustle, a side project where you want to have scalability if your product's a success, but you don't want to pay like a heroic cost if no one's using or converting, as was my case with Deployer. And finally, if you're a machine learning engineer, you want to create like a MLOps system where data scientists can just deploy models without the hassle of like creating new servers. You can easily do it programmatically. So everything that I do here is not through like the AWS console. There's a notebook where you can reproduce and change all the Lambda creation, invocation, and so on with Python code, actually. Now, why not go with serverless? The first is more of a general principle that I follow, which is if you're talking about like business, you should choose boring technology. So by default, just go with the technology that has more resources, whether people with experience or material online. And in this case, I would say the Flask server. I've seen Flask server powering applications that are literally impacting dozens of millions of dollars in revenue. And that just works. If you have very tight latency constraints, let's say you're doing like real-time ad auctions and spikes are unacceptable, Lambda is really not for you because you don't have a lot of control over the latency. If you provision concurrency, you're going to pay a high cost, so it's much better to just have a server there. If you need like flexibility to do like state-of-the-art deep learning, you want to run inference for LLMs on GPUs, this is the kind of stuff that Lambda is not going to allow you to do. Like, you got to use a more typical, like scikit-learn pipeline style of model. And finally, if your scale is absurdly high, Lambda is not going to be cost-effective relative to servers. So let's go over an actual example here. First, I'm going to be very brief on the machine learning part because this is not the focus. I just chose like this problem almost at random. We have a text classification problem with 20 classes. It's a news groups where it can be atheism, autos, hockey, and so on. And I just went with a text classification baseline, TF-IDF logistic regression, that is bag of words linear classifier, and I got a test accuracy of 85%, which is close to the state-of-the-art using deep learning of 90%. Just so you can understand exactly what is happening here, this is one random test example. So there's this post in this news group, and it's classified correctly as atheism, and this is a softball, right? Like there's atheism, God, atheist as keywords. And interestingly, there's also UK here below as a feature that goes towards this class. And now let's look how this actually works, how we can go from such a model to like an endpoint in a few seconds. I'm not going to actually run the code. It's already ready for us, but I'm going to stress the endpoint a little bit. And first, what is the Lambda function I'm actually using here? It's quite simple to the minimalist example. It just has more error handling, that's all. But we start with the model, the pickle loads to get the model. And then we parse the inputs, that is event. And then we call the model predict on the pickle load. And finally, return the model predictions as an output. And this is going to be interpreted by API Gateway as a HTTP response, so we can define status codes and other stuff, like the body. Now, as I said before, you should always go with the Docker path, and here it's how it looks like. It's also simple. You start with this base image from Amazon. They have different images for like different Python versions. You install the requirements with just good old pip install. Requirements are here, just like what we need, like pandas, numpy, scikit-learn, cloud pickle. And then we copy the artifacts into the image. So we're copying the predict script that I just showed you people, and we copy the model pickle inside the image as well. Just as a side note, you shouldn't really use a model pickle stored inside the image. You should probably, if you're serious about this, upload to S3. And the major reason is that if it's on S3, you can change the model without changing the Docker image. And finally, you define what is the handler. Here's the predict function. And now we can just see the code briefly. I'm not going to go over every line. You must be all very exhausted by now. And I don't want to bore you with like all the commands to like create the Lambda and the API gateway. You can always follow this later. I'm going to provide like a link for the notebook and blog post. But essentially, first, we dump the model using Cloud Pickle. And there is a good reason for using Cloud Pickle, not Pickle. I can explain later. We define some stuff, and we start doing the AWS commands, like IAM role and Lambda, and we have to like create, build, and push a Docker image to the cloud. We use the Elastic Container Registry. And then we do all the API gateway definitions, including like a usage plan with quote and so on. And after running all these commands, you have URL. I even forgot to like print this. OK, so we have an URL, which is created by Amazon. Of course, you could use a different DNS. But this is already working. So by just running those commands that I showed you here, you can go from model to endpoint in just literally like 1 minute. And this endpoint is ready to be used at scale. To have skin in the game, I'm making this endpoint public in the blog post, and I leaving the API key here as well. My friend from AWS, when he read the blog post, he was kind of shocked. But I explained that I have very strict quotas here, so you cannot bankrupt me if you try. But feel free to do it. And we can just try to like make some requests to those endpoints. I'm using the request library here, and just using the URL. This is just some basic headers, including the API key. And finally, like whatever test I want to run. Let's change this to like atheism and run this right now. It's going to take some time. It took 2 seconds. That seems very, very, very slow. And the reason is the warm start problem, or the cold start problem. There were like no Lambda instances running for this particular endpoint at the moment. But if you run again, well, it's much, much faster now. So as long as this instance is warm, it's alive, it's always going to be roughly around 150 to 200 milliseconds. And we can change as well, like the text here, hockey. It's going to get hockey, of course, but we can also make it more difficult. Montreal Canadiens. Also hockey. And this took 2 seconds, probably because AWS spawned another instance. You don't have control over this. So again, if you have latency considerations, this can be problematic. And again, you can always provision some concurrency. Now let's just go back to finish the presentation. You can leverage a lot of AWS functionalities in your favor here. For example, you can use CloudWatch as a monitoring dashboard. You could also, as I mentioned, use S3 to store your models. With CloudWatch, you can have alarms, logs, and so on. This does not cover the ML needs of our application. You cannot track accuracy as a metric, or you cannot track covariate shift. This is going to require a different solution. But from the, let's say, SRE perspective, AWS got you covered. And as just recapping some important tips and tricks, you don't have to load the model at every function call. I didn't mention this actually, but since the model was outside the predict function, the predict handler, it's just done once when the computing instance is created. So you pay up the price in the first call, but then subsequent calls are going to be faster. This is actually the recommended way to cache things with Lambda. Just put them outside your function. You can store the model S3 for better model management, like updating models, file history, and so on. You can leverage other AWS tools. You can use, for example, CloudFront for caching or your API gateway. And you can provision concurrency for stronger latency guarantees, but that's going to become very costly. And just some final takeaways here, just reinforcing the message. First, if you can, use boring technology. Go with a batch model, if that's possible. If not, go with a Flask server only go with, let's say, fancy technology if you have a strong, clear use case for it. But if that's the case, Lambda is a perfectly valid tool for ML deployment. And there are two major advantages. First, you don't have to maintain or scale a Python web server. And second, you only pay for what you use. And if you follow the link here, you can get access to the notebook and blog posts, and you can run this yourself. Thank you.
Any questions for Pedro?
Thanks for the talk. I think AWS has launched the SageMaker lambdas as well, where you can GPU compute for your lambdas. Have you tried this out? Does it work?
Oh, I wasn't aware of that, actually, so it's a nice tip. I don't really know if it works because I haven't tried, but in my experience, lambdas are not really like the best tool if you need to be close to the state of the art. I can say that with certainly because I use SageMaker for other needs, like regular GPUs, which is more standard. And even for that, I'm not, to be honest, very happy with it. There are other tools for GPUs which are cheaper, and you have access to higher-end, newer GPUs. So if you use AWS for this kind of, let's say, deep learning or more advanced stuff, you're probably going to be behind maybe a year, a couple of years, compared to the frontier of knowledge.
Okay, thanks.
Really great talk, thank you. Could you tell us a little bit more as an extension about how to record events that are happening? If we expose it as an API, right? What is the request and what is the response of the API itself? Did you think about it? And if so, what are the best practices in terms of recording the events that are happening behind AWS Lambda?
Yeah, good question. Depending on your volume, you could use SQS to send whatever logs you want to S3, or you can just leverage CloudWatch directly. So if you go to the Lambda function page, you have some metrics here and some logs. So you can see what's happening for recent invocations, and you can also access this programmatically. So CloudWatch does provide some functionality for logs, but you can also just write them to S3 and then access the logs via. You can put this in your ETL, so you can go to the data lake, or you can use Athena to just consume the logs directly. There are many ways, since it integrates very well with other AWS stuff. I think you would be covered log-wise.
Okay, if we have no more questions, then thank you so much, Pedro, and thank you for being here.
Thank you.